Hi everyone, my name is Harsha Sharma, and today I'll be talking about our work on optimizing network provisioning through cooperation. This work is in collaboration with authors from Microsoft Research India and Office 365 Substrate. Wide area network is expensive with an annual cost of hundreds of millions of dollars. There has been a lot of work done in the domain of traffic engineering, such as SWAN, B4, Pretium, and TVAR, which aim to improve network utilization by optimizing the control and data plane. On the other hand, network provisioning has received relatively less attention. Network provisioning precedes traffic engineering and is a longer-term process of planning out the network topology and capacity. Our goal in this paper is to do network provisioning optimally, and we show that our work is complementary to the existing work in traffic engineering. The process of network provisioning involves forecasting traffic demands, and the state-of-the-art network provisioning approaches compute peak or 95th percentile of the forecasted traffic demands and give that as an input to the network provisioning LP or simulator. It also takes as input the existing network topology. The idea is to minimize network capacity that needs to be augmented on top of the network topology to accommodate the forecasted traffic demands. And since link failures are common in wide area network, we also simulate link failures. And the network provisioning LP also simulates the underlying traffic engineering to figure out the routing and scheduling of the forecasted traffic demands. The final network capacity should be able to accommodate the forecasted traffic demand peak in the face of anticipated failure scenarios. For cloud providers, inter-data center traffic consists of traffic from both first-party and third-party applications. First-party applications are the applications which are owned and managed by the same cloud provider, whereas third-party applications are owned by a separate entity. In today's network provisioning pipeline, there is a firm separation between the application and the network. Network provider just observes the aggregate traffic pattern over time using network monitoring logs and makes forecasts using this implicit signal. For cloud providers such as Microsoft, Google, and Amazon, inter-data center traffic is dominated by first-party applications. Hence, we propose that the first-party applications can share richer explicit signals about their demands with the network provider, and then the network provider can do more informed network provisioning. For instance, instead of treating all application traffic as the same, the applications can differentiate between different classes of traffic and give explicit richer signals to the network provider, and the network provider can use these signals to do forecasting and provisioning. We term this as optimizing the provisioning plane as opposed to the control and data plane optimizations we have seen in the existing traffic engineering work. Now, what are these richer signals that the application can share with the network provider? We discuss this in the context of Substrate Data Engine, which is used widely by Microsoft services. We identify two broad categories of demands, immediate demands and deferrable demands. These categories also generalize across other applications, as we have seen in the existing work. Immediate demands are user-facing demands, such as this video call that we are currently having, and can be specified in terms of rate. Deferrable demands are a subpart of background demands, which can be deferred until a deadline. Some examples of deferrable demands in the context of Substrate Data Engine are load balancing traffic, which occurs when a server is at the risk of running hot on one or more resources, such as CPU, storage space, or I/O capacity, and needs to shed load to other servers. Periodic tasks, such as garbage collector tasks, time-driven deletions, etc. And server hydration traffic, which occurs when new servers are initialized with data from the existing servers. Deferrable demands can be specified in terms of volume and deadline. For example, 1500 TBs of load balancing traffic that needs to be sent within a deadline within a window of 7 days from the start time. There are also other SLA requirements such as availability. For example, an availability requirement of 3.9 means that the demand should be satisfied at least 99.9% of the times. So in the previous slides, we saw that how cooperation between first-party applications and the network provider allow first-party applications to share richer explicit signals about its demands with the network provider. Now we will see that how the network provider can utilize these richer signals to do more informed provisioning. We discussed two ideas for this. The first idea is to time shift the differable traffic to cap the peak. In the network provisioning slide, we saw earlier that the state-of-the-art network provisioning approaches compute the peak on 95th percentile and do provisioning based on that peak or P95. Whereas we propose that we find a lower capacity value, which is shown in red, such that had we provisioned only this much capacity, everything would have been fine since the traffic engineering would have moved the deferrable traffic into the valleys. And the flexibility of deferrable traffic allows the shifting from peaks to valleys. Note that we do not do real-time traffic smoothing. We are just estimating this minimum capacity, this tighter estimate of demand we need to have to ensure that all the demands are met. Then we do provisioning based on this tighter estimate of demand, this reduced smoothed peak. And this would force the traffic engineering to stay within this peak. Also, we do this at a much larger time scale as compared to the smoothing done by real-time traffic engineering. The second idea is to do informed redundancy provisioning. Consider two data centers, data center 1 and data center 2. And we want to provision capacity between DC1 and DC2 such that at least 100 Gbps of capacity is always available between DC1 and DC2. Then if we simulate 2 link failures, then we need to provision at least 3 links between DC1 and DC2, which would sum up to a total capacity of 300 Gbps. However, if the demands between DC1 and DC2 comprises of both immediate demands and deferrable demands, then we can do more informed redundancy provisioning. First of all, we need to provision full redundancy for the immediate demands, as the immediate demands cannot be paused or rescheduled. Hence, when there are no failures in the network, we send both immediate demands and deferrable demands. But when there are failures in the network and the deadline of the deferrable demands exceeds the time to repair, then we only send immediate demands and we pause the deferrable demands for the duration of the link failure. For example, consider a deferrable demand with a deadline of 15 days and the time to repair of the link is 2 days. Then instead of provisioning full redundancy for the deferrable demand, we pause the traffic, we pause deferrable demand traffic during those 2 days. And after the link gets repaired, we continue sending deferrable traffic. We continue sending deferrable traffic after the link gets repaired. And we also ensure that we are able to send the traffic that was paused during those 2 days after the link gets repaired. Hence, since deferrable demands can be paused for a substantial period, we could potentially avoid provisioning redundancy for deferrable demands. Now we will see that how we can augment our network provisioning to do this time shifting and informed redundancy provisioning. Going back to the network provisioning slide, we saw that simulating link failures is an important part of the network provisioning process. So here we discuss 2 types of link failure scenarios that we can simulate. The first type is point-in-time failure scenarios, which is up to K link failures. For example, the 2 link failure scenario that we saw in the previous slide. For immediate demands, point-in-time failure scenarios make sense since it does not matter for immediate demands that whether the link fails for 1 hour or whether it fails for 10 days. We still need to do full redundancy provisioning, and hence rate-based provisioning makes sense for immediate demands with point-in-time failure scenarios. Previous work such as robust validation of network designs, forward fault correction, and TVAR have also used point-in-time failure scenarios. Whereas in the context of informed redundancy provisioning and deferrable demands, we saw that we could potentially pause the deferrable demand during the link failure, and then we can continue sending it back after the link gets repaired. Hence, we need to consider the failure pattern over a time window for doing provisioning for the deferrable demands. And we do this using volume-based provisioning for deferrable demands. I'll be talking more about time series failure scenarios and volume-based provisioning in the next slides. Hence, we built Approv framework to implement the ideas of time shifting and informed redundancy provisioning. In Approv, we do network provisioning in a 2-step process. In step 1, we do provisioning for the immediate demands, and in the step 2, we do provisioning for the deferrable demands. For immediate demands, we do provisioning using the existing capacity provisioning approach of using rate-based provisioning, which takes as input the immediate demands and the point-in-time failure scenarios, and gives us output an interim capacity plan that should be able to accommodate the peak of immediate demands during the simulated point-in-time failure scenarios. On top of this, we do provisioning for deferrable demands. And for deferrable demands, we use volume-based provisioning, which takes as input the deferrable demands and time series failure scenarios. Volume-based provisioning is essentially a packing problem with the objective of minimizing the capacity provision subject to the deadline constraints. Hence, volume-based provisioning will schedule the deferrable demands during the non-peak hours, hence minimizing the peak, and during after the link gets repaired, hence minimizing the redundancy provision. The final capacity provision should be able to accommodate both immediate demands and deferrable demands in the face of failures, while ensuring that all the deadlines for deferrable demands are met, as well as the availability requirements are also satisfied. We talk more about availability requirements in the paper. In the paper, we have shown results using time series failure scenarios using past failure occurrences. And we also show results for a generative time series failure model. We generate time series failure scenarios to generate a combination of time series linked failures. And we leverage data of past failure occurrences to do that. The first step is to identify correlated link failures. For example, in the network topology shown on the left, link 1, link 2, and link 3 have correlated link failures, which could either be because of a shared power source or a router. And we group these links together since they have correlated link failures, whereas link 4 is in a different cluster. Now, for each cluster, we model time to repair and time between failure probability distributions. And to generate the time series failure scenario, we sample time to repair and time between failure values from these probability distributions. And to be more conservative in our approach, we fail all the links in a cluster simultaneously. Hence, we lose more capacity and we end up provisioning more capacity, which means that we are being conservative in our approach. Now, I'll share the results we have from applying all these techniques. We use data from substrate data engine where a major part of traffic is load balancing and server hydration traffic. The y-axis here shows percentage capacity savings. The left figure is for Asia Pacific and the right figure is for North America region. And here I only consider load balancing traffic as the deferrable traffic. For Asia Pacific region, we get around 20% capacity savings with only time shifting, and 30% capacity savings with both time shifting and informed redundancy provisioning. And in North America, we get 5% capacity savings with time shifting and 25% capacity savings with Approv, which is both time shifting as well as informed redundancy provisioning. As we can see, the gap between time shifting and Approv is higher in North America, which means that we get higher capacity savings in North America because of informed redundancy provisioning. And that is because, as it can be seen from the CDF of time to repair values for North America and Asia Pacific region, North America region links have lower TTRs as compared to the links in APAC region. And that is because North America has more LAN cables, whereas Asia Pacific region has more subsea cables, which take longer time to get repaired. Because of these low TTR values, we end up saving higher capacity. We end up saving more capacity in North America region, since we can potentially pause the deferrable traffic for that shorter duration of time and avoid provisioning redundancy for the deferrable demand. Now I show the capacity savings with both load balancing traffic and server hydration traffic considered as deferrable traffic. We get higher capacity savings in the Asia Pacific region. And that is simply because there is more server hydration traffic in APAC, because a larger set of servers were forecasted to come into Asia Pacific region at the same time. Now, these capacity numbers are dependent on the deadline values for deferrable traffic as well as the availability requirements. So in the next slide, I show how the capacity provision varies with deadline and availability. As expected, capacity provision decreases as we relax the deadline and the availability requirement. There are also interesting trade-offs, such as a demand with a deadline of 2 days and an availability requirement of 3 nines requires similar capacity provisioned as a demand with a deadline of 12 hours and an availability requirement of 2 nines. Applications can hence make interesting trade-offs between deadline and availability. To conclude, cooperation between first-party applications and the network provider allow richer information sharing between the first-party applications and the network. And then the network provider can utilize these richer signals to time shift deferrable traffic as well as do informed redundancy provisioning, which results in capacity savings. In the end, we show approximately 30% and 40% capacity savings in North America and Asia Pacific regions, respectively. Thank you so much for listening.